Let's consider a few examples on matrix multiplication to understand the idea of multiplication easily. Let's take a matrix A as 2, 1, 0, 3, 2, 1, 1, 0, 1. So what is the order of this matrix? Yes, this is a 3 by 3 matrix. Similarly, let us consider a matrix B 1, 2, 2, 0 and 3, 1. So what is the order of this matrix B? Yes, it is 3 rows, 2 columns. Now, is this multiplication compatible? How do we verify that? The number of columns of the first matrix must be same as the number of rows of the second matrix. Yes, the columns in first matrix is 3 and the number of rows in the second matrix is 3. Therefore, this product is defined. So, how will be the product A into B? The first row entries multiplied with the first column entries to get the first element in this. That means it should be 2 into 1 plus 1 into 2 plus 0 into 3. Similarly, how do we get the second entry? Yes, it would have first row, second column will give us the first row, second column entry here. So let us multiply the first row with the second column of B. Then it is 2 into 2 plus 1 into 0 plus 0 into 1. We multiplied the first row of A with the second column of B. Similarly, how will be the second row of first column entry? Second row of A must be multiplied with the corresponding elements of the first column of B. That means this is 3 into 1 plus 2 into 2 plus 1 into 3. Similarly, how will be the second row, second column entry? The second row of A multiplied with the second column of B, it would be 3 into 2 plus 2 into 0 plus 1 into 1. Next, how will be the third row of first column entry of the product? It would be the third row of A multiplied with the first column of B. That would be 1 into 1 plus 0 into 2 plus 1 into 3. Similarly, how will be the third row, second column of the product? It would be third row of A multiplied with the second column of B. 1 into 2 plus 0 into 0 plus 1 into 1. So how will be the product? It would be 2 plus 2, 4, 4 plus 0 plus 0. So 4, 3 plus 4, 7 plus 3, that would be 10, 6 plus 0 plus 1, that would be 7, 1 plus 0 plus 3, that would be 4, 2 plus 0 plus 1, that is 3. Now we are able to find A into B. Just for the sake, can we calculate B into A? As the number of columns of B, which is 2, is not equal to the number of rows of A, which is 3. So B into A is not defined here, right? So in this A and B, we can find only A into B product, but we cannot find B into A product. Now let's consider another example here. Let us take A as a matrix which has entries 1, 2, 3, 4 and consider another matrix B which is having entries 5, 6, 8 and 9. Now what is order of the B matrix? It is 2 by 2 matrix. What is order of A matrix? It is also a 2 by 2 matrix. Now as the number of columns of A is equal to the number of rows of B, we can multiply A into B. So how will be the product A into B? It will be the product of the matrices 1, 2, 3, 4 multiplied with 5, 6, 8 and 9. Then first row of A multiplied with the first column of B would give us 1 into 5 plus 2 into 8. Then similarly, first row of A is multiplied with the second column to get the product. So first row, second element, that would be 1 into 6 plus 2 into 9. Similarly, the second row of A is multiplied with the first column of B to get the second row first element. So this would be 3 into 5 plus 4 into 8. And the second row of A is multiplied with the second column of B to get the second row, second column element in the product. So this is 3 into 6 plus 4 into 9. What is this matrix A into B now? 5 plus 16, that would be 21. 6 plus 18, that would be 24. 15 plus 32, that is 47. 18 plus 36, that is 54. So we got A into B matrix. Now if you look at the number of columns of B are again same as that of the number of rows of A. Therefore B into A product is also possible here. How will be the product B into A? This will be the product of 5, 6, 8, 9 multiplied with 1, 2, 3, 4. How does this product gets effective? Yes, the first row, first column is the product of first row of B with the first column of A. Then it would be 5 into 1 plus 6 into 3. Similarly, how will be the first row, second column element of product is obtained? The first row of B multiplied with second column of A would give us 5 into 2 plus 6 into 4. Then again, how do we get the second row, first column entry? It would be the second row of B multiplied with the first column of A, which would be 8 into 1 plus 9 into 3. And the second row, second column entry is obtained by multiplying the second row of B with the second column of A. That would be 8 into 2 plus 9 into 4. How much is this matrix? Yes, this is 5 plus 18, that is 23. 10 plus 24, that is 34. Similarly, 8 plus 27, this is 35. And 16 plus 36, 52. Now if you look at here, one important observation is both A into B exist, B into A exist, and both of them are 2 by 2 matrices only, right? But still, A into B matrix is not equal to B into A matrix. Though both of them are defined, A into B is defined, B into A is defined, but still A into B product is not same as B into A product, right? That is a very important observation in matrix multiplication. They will not in general follow commutative property. Let's look at some of the important properties satisfied by matrix multiplication. The example last which we have seen indicates this property only. Matrix multiplication is not necessarily commutative. That is, A into B is not necessarily equal to B into A, even though both of them might exist, right? It is also a problem to have an existency, but even in case if they are existing, they may not be equal. The matrix multiplication is associative. Now this is a very important observation. When we consider matrix A as Aij of order M by P and the matrix B of order matrix of entries Bij of order P by N, so that the number of elements of P by Q, so that the number of columns of A is maintained equal to that of the number of rows of P. And we'll take the third matrix C, which is Cij having order Q by N, so that again B into C product is also compatible. Now how will be the product B into C and A into B as per the requirement? The matrix A into B will be U of IL. And how will be the order of the A into B product? Yes, it would be of order M by Q, where how do we define UIL? We know the summations. It is sigma K is from 1 to P, the number of rows and columns which are equal. K runs from 1 to P, Aik into B, KL, and this is a matrix of order N by Q. And how will be the product B into C? Yes, this will be a product of elements of the form V, Kj. And what will be the order of B into C? Yes, as a Q, that is the columns of B are equal to that of rows of C. The final product would be of order P by N. And how do we express this as a sum? This would be entries of B into C, which are of the form sigma L runs from 1 to Q, BKL into C, LJ, right? Of order P by N. Now we have defined both B into C and A into B. How will be the product A times BC? This is a product of the matrix A with the product of the matrices B and C. So this B and C, B into C is treated as a single matrix. Then we are going for a product of A with the product matrix BC. Then it would be by summation notation. It is sigma K runs from 1 to P, Aik into V, Kj. But we have a notation for V, Kj in the form of sigma. Then when we replace that, this is sigma K equal to 1 to P, Aik into sigma L runs from 1 to Q, BKL into C, Lj. As the summation is on a finite series, this can be now replaced as the summation can be altered. This is entries of the form sigma L equal to 1 to Q times sigma K equal to 1 to P, Aik into BKL times C, Lj. Now what is this entry here? Sigma K equal to 1 to P, Aik into BKL is the element UIL itself. So can we rewrite this as sigma L is from 1 to Q, UIL into C LJ, but this UIL denotes an element of A into B. So this is nothing but the matrix product of AB taken with C. So matrix multiplication is associative over three elements A, B and C. Now, by definition, A power n is A multiplied n times, and this will exist only provided A is a square matrix. Now, if you can clearly see, A is a matrix of order, say m by n, then when can be A into A defined? A into A is defined provided m equal to n, right? So that the next product when we write, the number of columns of the A, first A, should be same as the number of rows of the second matrix A. That means these two m and n must be equal. So whenever A is a square matrix, then only a power of A exists. And how will be the power? A power n is defined as A multiplied n times. So in general, if you write A square, this is going to be A multiplied with A. Whereas when we write A to the power of 5, this means A multiplied 5 times. Now all the exponential results of number system do follow in matrices. A to the power of P whole raised to the power of Q is same as A to the power of P into Q, a well-known result from algebra. Now similarly, A to the power of P into A to the power of Q will be A multiplied P plus Q times. So A to the power of P into A to the power of Q will be A to the power of P plus Q, and in all the cases A must be a square matrix. Now similarly, matrix multiplication is distributive over elements addition, that is A times B plus C will be equal to A into B plus A into C. If you look at A taken as Aij of order m by n, then how should be B a matrix? B matrix must be of the entries Bij, which should have the number of rows same as that of the number of columns of A. So let us call this as n by P. Now B plus C must be defined. So how should be the matrix C? Yes, this should have entries Cij. But for B plus C to be defined, even C must be of the same order n by P. Then A times B plus C would be same as writing sigma j running from 1 to n. Yes, Aij element multiplied with Bjk plus Cjk. Now as these numbers Ij, Bjk and Cjk are all real numbers, they follow distributive property by themselves. So can we rewrite this as sigma j runs from 1 to n Aij into Bjk plus sigma j runs from 1 to n Aij into Cjk. But how is this product here? This sigma notation says this is the matrix product A into B with this product A into C, right? So matrix multiplication is distributive over matrix addition. If A is a square matrix of order m by m, then Im, that is the identity matrix of m by n, is the multiplicative identity. That means A multiplied with I will be same as I multiplied with A, and both the products would be equal to EA. Let us observe this. When we take a matrix A as A11, let us take the matrix A as Aij of order m by m. Then how will be the matrix I? Yes, I will be a matrix of the form Bij, again of order m by m, square matrix. But what is the characterization of Bij? Yes, where this element Bij will be 1 if I equal to j, and it would be 0 if I is not equal to j, right? Then it is an identity matrix. Now what happens when we multiply these two matrices? A into I would be matrix entry of sigma j runs from 1 to m. Yes, Aij into Bjk. But when you expand this on a sigma notation, this would be Ai1 into B1k plus Ai2 into B2k plus Ai3 into B3k, so on up to, how long does this process goes on? Aim into Bmk. In between them there will be only one element for which you will get Bij. All the rest of the elements B's would become 0. So when will it become 1? When I and j are equal, then this will become 1. That means what do we get? Aii into Bii. As Bii is 1 and all the rest of them are zeros, this would again give us Aii. So what are we left with? Only this element would be left and the rest of the elements would be zeros. So this will denote the matrix A again. So A into I will be same as that of A. You can again follow the same thing for I into A. Let's look at another important property of multiplication in matrices? If A and B are two diagonal matrices, then their product is another diagonal matrix whose elements are the corresponding product of the elements of the two matrices. Now to understand this, suppose let us assume A is a A1 0 0 0 A2 0 0 0 A3. That is a diagonal matrix. When we denote this, how is the matrix A? It is diagonal matrix A given by A1, A2, A3. Now similarly, let's consider another diagonal matrix B of the same order, that is B1 0 0 0 B2 0 0 0 B3. Then B can be denoted as diagonal B given by B1, B2, B3. Now how will be the product of these two matrices? When we write A into B, yes, A1 gets multiplied with B1, the first row multiplies with the first column. You have only A1 into B1 added with the remaining two elements are zeros. Now similarly, when you look at the first row multiplied with the second column, all the entries are 0. A1 multiplied with 0, 0 multiplied with B2, 0 multiplied with 0. So this entry would be 0 plus 0 plus 0. How will be the first row third column? Yes, A1 multiplied with 0, 0 multiplied with 0, 0 multiplied with B3. That will be 0 plus 0 plus 0 again. Similarly, this element also would be 0 plus 0 plus 0. The product of second row with first column. And the second row with second column would be 0 with 0, but A2 plus B2, that is A2 into B2 here with 0 into 0, that would be 0. Then again the second row third column would be 0 plus 0 plus 0. The third row first column would be 0 plus 0 plus 0. Third row second column is again 0 plus 0 plus 0. But look at the third row third column. When this row of A is multiplied with this column of B, we get 0 into 0, 0, plus 0 into 0, that is 0, with A3 with B3, that is A3, B3. So how is this matrix? Yes, this is again a diagonal matrix having A1, B1, 0, 0, 0, A2, B2, 0, 0, 0, A3, B3. Now how are the entries here? The product of the two diagonal elements of A and B are present at the case. So can we write the product is diagonal AB, which is given by first diagonal entry into the first diagonal entry of the second matrix, A2 into B2, A3 into B3, right? That's what this result says. Now what do we mean by diagonal matrix raised to a power n? By this result, if B1 is same as that of A1, then that is A1 into A1, that is A1 square, A2 square, A3 square. Similarly, when we raise it to the power m, the diagonal elements get raised to the power m, right?